All right. So we are on slide number 12 of 7th lecture now. On this one, basically we are going to continue to talk about 11E. So there are some standards which are really important in the 11 series. 11E is the next important one, which actually does the quality of service. Now in the 11E, what they have done is they have put priorities. Basically, so instead of having one priority, they have 8 priorities, but they have only 4 queues. So really there are 4 priorities in that sense. And what they have done is that the previous algorithm, which consisted of a beacon followed by the point coordination function followed by the distributed coordination function, now they have extended that to a little bit more complicated. And one thing about the point coordination function is, remember, point coordination function was for the contention free period where we allocate you some bandwidth beforehand, so there is no contention. While it is in the IEEE 11 standard, 802.11, it is not implemented in any products, so it's more of a theory than practice, ECF. But since the standards, so basically in the new standards 11E, this DCF part and the part we just discussed a minute ago, that is the DCF part, that you have to declare you have to wait for nav to expire, then you have to wait for the diffs, then you have to do the back off. That has been extended to 4 different queues, maybe 8 different priorities. And so it is called hybrid. Actually there are 2 parts. PCF has become HCF, which is hybrid coordination function, and DCF has become EDCF, which is the enhanced DCF. Okay. So now when you hear a beacon, after that there is a contention free period, which is called HCF. After that there is an enhanced coordination function, and then there is another contention free period, and then there is another enhanced coordination period, and so on and so forth. The reason they have to have so many is because the beacon interval might be too long, and these point coordination functions or the time critical functions may not want to wait that long, so they have multiple of these as opposed to just having one. So these are contention free periods. Second thing, so basically this adds is, first thing it adds is that in this HCF, second thing it adds is direct link. So previously, if you had an access point, all the packets from A to B have to go from A to access point, from access point to B. Okay. Now if you get an equipment which is 11E compliant, then you can go from A to B directly. And so you just announce, even with the access point being present. In the ad hoc mode, obviously you could say I want to go from A to B, but in the access point case, everything went through access point, central point. But now you could set up a direct link. And third thing is that the frame bursting. Previously every frame was followed by an acknowledgement. Now you could send a frame and say I don't need acknowledgement for this one. You can send second frame, third frame, fourth frame, and then you say I need the acknowledgement. So you get the whole acknowledgement for all 4. So it's like having a bigger window than the window of one. And that is particularly helpful because with high speed networks the frames are very, very short, and so you don't want to get acknowledgement after every little frame. So that is frame bursting and the group acknowledgement. And multiple priority levels. So now the multiple priority levels actually are by just extending all these parameters that we had before on the back of the CW min, CW max, why are we calling them BW min? I think this should be probably CW min. So for each priority we have a different CW min, CW max, and then we have the back-off timer for each priority, and then there are this interframe spacing, which was your diffs, which is different. All right, and then the duration for each of these. So now basically, if you have higher priority, they have a smaller back-off, and the lower priority have larger back-off. So obviously CW min and CW max for a higher priority would be much bigger than for the lower, for lower priority would be much bigger than for the higher priority. So higher priority may just draw a back-off random number between, let's say, 1 and 3, while the higher priority might draw between 63 and 128, something like that. So that ensures that the higher priority frames get through first. And this is their, this is now called AIFS, which is the arbitrated interframe spacing. And so that is actually, there are 4 numbers here. This is smaller than the other ones. So when the medium becomes available, the higher priority weight less for what we used to call diffs. And the transmit opportunity is the duration and for which you can transmit, and each priority has a maximum size for which you can transmit. They don't want higher priority to be transmitting for very long, so then there is those number TXOP. And then there is a back off 1, 2, 3, 4. Those are basically your timers, which are random numbers. All right. So the summary of this thing is that the EDCF is very similar to DCF, except instead of 1 parameter set, you have 4 sets. All right. And higher priority traffic has to wait less than the lower priority traffic, as you expect. And so basically when a frame comes in, the station decides which queue it goes into, and once it goes into that queue, then basically it uses that parameter to sense the medium, to grab the medium. Is that clear? Now diffs is called what? AIFS. So the name for the diff has changed, and CW min and CW max are still CW min, CW max, and their values are such that the higher priorities have to have a lower CW, right? So their random numbers comes out lower. What else? This okay. Now bursting is the next feature where you allow to send multiple frames. So you might send data, ACK, data, ACK, and then wait and all that, and there is a limit to how much you can do that at 1 priority, because you don't want to starve the lower priorities. So there is a maximum time limit before which you have to give up the medium. Okay, and the higher the priority, the lower the burst size. Basically, so that not everything becomes high priority, otherwise everybody wants to be high priority. So voice and gaming has high priority but small burst size. Video and audio have lower priority. Video and audio have lower priority but larger burst size. So basically priority and the burst size go opposite, right? And what is not shown here, actually there are two different things. Let me see. There are two different things. Frame bursting and group acknowledgement, they are two different things. Okay? Two different things in the sense that what I have shown here is frame bursting. So I am transmitting multiple frames. However, each frame is acknowledged. So this is not a group acknowledge. Another alternative would have been to have multiple frames and then one acknowledgement. That would be group acknowledge. Right? So these two are independent concepts. With multiple frames, frame bursting, you get the permission when you do the RTS. In that you say, I want to send for the next 100 slot units. If you are allowed, if your TXOP allows, you can say I want to send it for the next 100 slot units, and you could send 5 frames in that 100 slot units. And so you don't have to do TS, RTS, and CTS. So the frame bursting means that you do RTS, CTS once for a whole bunch of frames. And the group acknowledge means that you do one acknowledgement for a whole bunch of frames. Alright, so they are trying to minimize the overhead at both ends. The RTS, CTS overhead and the acknowledgement overhead. Yeah, your question now.
My question regarding to the last two lines. Voice and gaming have high priority but small burst size. How does a circuit know information about the data? I mean, with all the layers of abstraction, shouldn't they be separate? So unless it's a dedicated line, how else would you know that the information passing is voice gaming or video audio? Yeah.
Now this is actually always a question as to how do you know what is this one. And the standard technique nowadays has been to use look into the other layers overhead, other layers headers, and basically by the port numbers. If it is an RTP packet, which is a real-time transport protocol, you look inside and then you do something and you figure out that this is high priority.
Doesn't that contradict the OSI layer then?
Yeah, so that is already contradicted. So one of the things that is happening is that for wireless networks in particular, you need cross-layer information, as we call it. So there is a concept of cross-layer coordination, where the higher layers would benefit very much by knowing that they are going over wireless or not going over wireless. Similarly, the wireless will benefit by knowing from the higher layers. So there is this thing about crossing the boundaries of the layers. All right. So here are the 4 priorities: background traffic, best effort traffic, video, and voice. These are the CW min. CW max is some value. The same value is used for these 2 priorities, but higher value is used but a different value is used for these 2 priorities. CW max value is given here. AIFS, these are the diffs value. So you can see the voice has the highest priority and their AIFS is lowest. And this is the TX up limit. This is the maximum nav that you could declare. And so this is 3 millisecond, this is 6 millisecond, and this is infinity. All right, there is no limit on the background and the best effort. All right, so we have finished the so-called 802.11e. 11e is the QoS standard. Just to summarize again, is the QoS standard, and it allows several new things. First of all, it allows 4 priorities. Then it allows multiple frames transmission by one RTS CTS thing. It allows multiple frame acknowledgement, and then basically it has more about those real-time traffic also. Again, we don't implement HCF, so it's not worth talking about. Hybrid coordination function was there in the first picture, but nobody implements it. So we just talk about the EDCF, which is the enhanced DCF. And enhanced DCF basically 4 priorities, which means we have 4 diff values, 4 CW values, and so on. All right. We will try to. So I don't know. Did you did you find a good reference for this? Can you find a good reference for this? Yeah. So I actually got all this from a book published by IEEE, and I don't know whether that is in the reference list. I have to double check that one.
There's no good reference. There's no good one reference.
There's no good one reference. Yeah. So I will check if I can find. Otherwise, Wikipedia is generally good, but I haven't checked Wikipedia for this, so I don't know.
No,
it's not there.
Wikipedia doesn't have anything.
Okay. All right. So we have plenty of books. I will have to just check on those books. Anyway, so with that, we move on to the next topic, which is power management. And power management is very important in wireless, and we will see it in every standard that we talk about, starting with this one. And basically, the scheme works as follows in all the standards. Is that a station, when they want to save their battery, they say, I'm going to sleep. They tell the base station generally that I'm going to go to sleep, and the base station then saves their frame. If a frame comes to them, the base station saves it, and every so often the base station announces, basically in the beacon, it announces that I have frame for station number 1, 5, and 3. And if station number 1, 5, and 3 wake up, or any one of those wake up, they just say to the base station, look, I am awake, please give me my frame. They get the frame and then they go back to sleep. Either that, or 135 can wake up and say, well, we have any frame for me, and if there is a frame, the base station gives them the frame and then they go back to sleep. So either way, the sleep coordination requires coordination between the base station, or the access point in this case, and the sleeping station. Access point, if knows that the station is not off. See, there are 2 kinds of stations. One, the station which have gone away forever, and the second, the stations which are sleeping. Sleeping stations are really here, but they're sleeping, right? So they are treated differently than people who have not come into this room at all, or walked out of the room, right? So let's see power management. The station tells the base station its mode. It says I'm in the power saving mode. I'm going to go in the power saving mode, and the mode changed by the power management bit in the frame control header. So every frame that is sent has a frame control header. We saw that in the beginning, just before the duration field. In the frame control header, there is one bit which says, look, I'm going to go to sleep. And after that, any packet that are received are buffered, and the access point broadcasts the list of stations with buffered packets in its beacon frame. In its beacon frame, there is a bit map. So let's say there are 20 stations in this network. There is a bit map of 20 bits. Each bit indicates for whom I have a frame, or the access point has a frame waiting, 1 or more frames waiting. So when you wake up, you listen to the beacon, and if the beacon has your bit set, then you just ask the base access point for that frame. All right. So that is the traffic indication map, TIM. The subscriber station, SS, subscriber station, this is a mobile station. Sometimes we call this mobile station, sometimes we call it subscriber station. sends a PS pole message. PS is the power save pole message to the access point, which sends one frame, and so access point will send one frame. The more bit in the frame header indicates that there are more frames. So every frame also has a frame control header in which there are many bits. One of them was, we already saw, was the power saving bit, but there is one bit called more bit, which tells that this is one frame, but I have more frames for you. Alright? So please stay awake. I'm going to send you one more. With 802.11e unscheduled automatic power save delivery, SS transmits the data or null frame with power saving bits set to 0, and the access point transmits all buffered frame for the SS. Now with 11e, it can send multiple frames, right? And therefore all of that can be done in one sweep. Whenever you wake up and you ask for a frame, you get all of the frames. With scheduled APSD mode, access will transmit a pre-negotiated time schedule and no need for polling. So now there is there is another mode for sleeping here, and that is the mode where we negotiate that you will wake up every so many milliseconds. At that time, basically you wake up and we will give you all the frames. There is no need to poll, as opposed to in the unscheduled polling where we will just listen for the beacon and figure it out. Alright? So here you just say, well, I am going to be off much longer now. So the thing is, this allows much more savings because you don't have to wake up at every beacon to listen to your bit pattern. Hybrid APSD mode, where PS poll for some and schedule for other categories. So you also have hybrid mode. Now here is the thing, this is all 11 and I am not sure which part of this is implemented. And this hybrid thing reminds me again of something. So what happens is, now there is a hybrid mode where you allow both, and I don't know whether all the products implement this mode or not, because this is the kind of thing which goes on in IEEE. In IEEE they put everything, and then Wi-Fi group will remove much of this stuff, simplifies lots of stuff, right? So for example, this whole PCF and HCF concept is in 11 but not in Wi-Fi. Similarly, this hybrid APSD mode, I am not sure. Alright? So anyway, there are two kinds of modes. In one mode, you listen to the beacon, you find your bit on, then you say, give me my frames, and you get the frame, right? In the scheduled mode, you just say, I will come back up after so many milliseconds, and then you come back up at that millisecond and you get your frame. Alright? There is no need for polling. So this is polling less, and that is one with polling. And obviously the first mode is already implemented. Basically the stations do go to sleep, and their times are announced in that map, so that I know is done, but I am not sure about the other parts, whether it is implemented or not. Alright, so it's clear as to how we save batteries. Before I move to the next slide. Okay. Then we move on to the next new standard, 11N. 11N stands for next generation of 11, actually, which is just convenient. It happened to be N. Huh? You don't have that slide? I printed 3 sets, right? Chapter 7. It ends at 20. It ends at.
Starts at 21.
Okay, let me just double check before I lose anything. So you don't have 17, and then what you have? Start with 20. Oh, okay. All right. Last week I gave you up to 16, And this week I gave you from 20?
Yeah.
Last class?
Right.
Okay, that was my mistake actually. So I thought I gave you 10 is up to 20. I mean, so that's why I didn't print. Okay. All right, we will,
I don't need notice either.
yeah, we will print it and give it to you. Or you can just go and download it too. Right now it's not up, but we'll give it to you next class. What is the next class? Monday? Yeah, next Monday we can give it to you. Before I do this much, let me just see that my recording is going on. Yeah. Okay. Okay. All right. Sorry for that mistake. There were too many handouts to print today, so I got confused. All right. 11N. 11N is 4 to 5 times faster than ARG, and the reason this is 4 to 5 times is because there was lots of question mark about some features which we'll talk about in a minute. So first thing is, it uses a code which is much better. So it uses 64 QAM with 5.6 code rate. What does that mean? So you remember QAM. We discussed QAM here in the file layer, and QAM was 16 QAM, and then we had 64 QAM, 256 QAM, and so on and so forth. As the time passes by, we are able to do higher level QAM because of the digital signal processing. So right now this is the limit. This standard is brand new, so it shows you right here that the limit is 64 QAM for low prices. Actually, you can always do 128 and 256, but that would be generally done for military, which has unlimited money. For most of us who want $5 device, 64 QAM is the limit. So 64 QAM with 5.6 code. So basically 64 QAM gives you 6 bits per hertz, but you only use 5 bits. 5 bits you use, and the 6th bit is used for error correction. And 2 spatial streams. So 2 spatial stream is this MIMO thing we talked about. 2 streams in parallel. 40 megahertz channel. That is another feature, which is that instead of having one channel, you use 2 channels. So use channel 1 and 6 together. So instead of 20 megahertz, you use 40 megahertz. And 400 nanosecond guard interval. That is the interval between the transmissions or frames. Gives you 270 megabits. Now, having said all this, not everybody agrees that this is what needs to be done. So you might get an 11N which doesn't do 40 megahertz. Alright, there was a big discussion about 40 versus 20, because with 40 what you're going to do is, if everybody started using 40, there are only 3 channels. Remember, 3 non-overlapping channels, 1, 6 and 11. If everybody started using 2, then nobody else can do anything much, So obviously 2 people cannot do 2 at the same time, right? So this 40 megahertz is there in the standard, but there was a big discussion whether this can be done all the time. MIMO is kind of always done for all 11N devices. They have multiple antennas, and I have shown you some here. And the major components, so these are the 10 major things that the 11N does. First thing it does is better OFDM. Better OFDM, and which means the QAM 64 coding, and it gives 65 megabits instead of 54 megabits. Higher code rate. So that was the business of 5/6. Code rate of 5/6. Previously we probably did 2/3, now we are doing 5/6. So that gives you better than 54. Second thing it does is space division multiplexing. So space division multiplexing is how much parallelism can you have, up to 4 spatial streams. So you could have up to 4 antennas. Diversity, more receive antennas than the number of streams. and select the best subset of antennas. So it also allows you, while the streams could be 4, you could have 8 antennas, for example, and then take the 4 best out of those 8 antennas. Beam farming, we talked about beam farming. Anybody remembers what is beam farming? What does it allow you to do? Dynamically direct. Right? You can change the direction by the seconds, by the milliseconds. Focus beam directly on the target antenna. MIMO power save. Use multiple antennas only when needed. So you might have 4 antennas, but each antenna requires power, so you may just use 1 antenna. But if you need more traffic, if suppose you get a lot of traffic, then you can use 2 antennas, 3 antennas, 4 antennas. So you can put antennas on sleep. Right? Not the whole station. You could put the whole station on sleep too. So basically, so that is another flexibility we have with multiple antennas. Channel bonding. Channel binding is basically this using 2 channels at the same time. So we transmit on both channels. Aggregation, transmit bursts of multiple data packets. This was already there in EDCF. Short guard interval, and so we wait smaller interval before we start the next frame. 400 nanoseconds instead of 800 nanoseconds. Reduced interframe spacing, and green field mode where eliminate the support for ABG. So here is what happens is that most of the time if you buy an equipment, it has to support the older standards as well as the newer standards. And that reduces the speed, because if you have to support A, B and G, then many of these spacing etc. will not work. And it turns out that if you have a mixed clientele, so for example you have some stations which do not understand N and some understand N, what will you get overall? Not understand N basically. You get the lowest speed of all. And so if you have some stations which understand B and don't understand G, but you have a G, rest of them understand G, what do you get? You get a B. So that's the thing, is that if you either you upgrade everybody to the latest highest speed, or you get the lower of the 2 speeds. Is that clear? Right? If you have mixed stations, which is always the case, when you have mixed station, you get the lower speed. And so if you don't support for ABG, then you get all this 200 megabits stuff with all these special features. But if you have other stations, then you get lower speeds. All right, that's all there is to say about 11N. Sorry you don't have the slides, but we will provide you on Monday, or you can print it out from the website. Okay, any question about 11N? Any of these features are not clear?
Can you go to the previous page? What are the 2 spatial streams?
What are the 2 spatial streams?
Yeah.
No, all this is saying if with 2 spatial streams you get 270, but the standard allows up to 4 spatial streams, right? So a spatial stream, if you remember MIMO.
Right, because it has 4 quadrants, right? So
No, 4 rays. Let me call it this way. If you remember MIMO discussion, in MIMO if you have multiple antennas, so if you have only 1 antenna, then only 1 spatial stream can go, from this antenna to that antenna. But if you have 2 antennas, then you can have 2 spatial stream going, 1 from this to that and 1 from that to that one, right? If you have 2 by 2, you have 4 spatial streams. Is that the question? Does that answer your question?
okay, so now is that a 2 or is that a 4?
No. See, the thing is, this is not the limit. This is saying that you can get 270 megabits with this set of parameters.
Okay.
Right? And it allows up to 4 spatial streams. And remember, with 4 spatial streams, you just don't get twice as much. of 2 spatial streams. Remember, we told you that if you have 2 by 2, that is 4 spatial stream, but you get only factor of 2, because you get almost the minimum of the 2 numbers. If you have 2 antennas here and 3 antennas here, you have 6 spatial streams, but you will only get factor of 2 because you get the minimum of 2 and 3. This was in the MIMO discussion, right? Any other question about 11N? All right. Then there is 11P, which is wave, wireless access for vehicular environment. Basically, this is a standard which is I had the standard status in the previous slide. Let me just double check the status. P. This is not approved yet. So this will be approved in November 2010. So this is still in works. I mean, it's still in development. So this will allow you to exchange the data between the vehicles and the roadside infrastructure. And it can be used for toll collection, commercial transactions, safety services, and the main thing is that it allows you a speed of 200 kilometers per hour. I think that's too high a speed, but anyway, for up to that speed, up to 1 kilometer. That is the distance up to which they cover. Basically, every standard when you design, see previous 11 standard, for example, were I think more like 100 meters or 200 meters, but this is longer. Right. But here's the thing, though. I mean, I don't want to say access point because I will have to verify. This might allow ad hoc mode, where you can talk from one car to the next car. In that case, the distance between the 2 cars. Right? And so there is something called dedicated short range communication, DSRC standard. So this 11P is used in the lower 2 layers of that standard. It uses 5 to 10 megahertz channel at 5.9 gigahertz. So this frequency is higher than 2.4, and the channel size is smaller. And I don't understand why did they select smaller channel sizes. Actually, there are 2 things which are different here, and I have to figure it out. One is that this frequency band is not the complete 5 gigahertz band. So the previously which we had shown you the frequency band that was ending at 5.85. In some slide I had shown you, you have probably the handout from the previous one. I will not go back to that one, but so this is higher end of that 5 gigahertz spectrum. They have selected especially for this reason, and then they have selected a smaller channel. So the standard is not out yet, but this is just, right now it is making quite a, let me say, quite a bit of wave, in the sense that I see lots of papers being published, quite a bit of activity in this area. Then the next standard to know is the fast BSS transition, and this allows you to move from one access point to the next access point without breaking. So this is just the same way like it does on the cell phone. When in the cell phone, when you are driving, you really are passing from multiple base stations, but you never know because your call continues. Similarly, on 11, but on 11, right now, when you move from one access point to next access point, the call disconnects. But if they implement 11R, then you will be able to move quickly without losing the connection. Then there is a mesh mode, 11S, and the mesh mode means that one station and the signal can go from one station to the next station. So for example, here there is a home network, and the traffic which is coming from somewhere else could be sent from this home to that home, from that home to that home before it reaches to this home. So that is called the mesh mode, and it's generally used by military and the emergency people because they may not have base stations, and they are not allowed to have base stations, particularly the military people. If they have base station, the first thing that will be bombed is the base station, and therefore they want to really run in an ad hoc mode in some sense. And so this is the mesh mode, is a special mode where basically you go from one station to the next station. You could also do in the enterprise where you could have multiple buildings which could be transmitting stations, transmit traffic from one to the other. And so 11S is has the facilities for this. It has special security because the traffic is going through other people's home, other people's devices. So for example, your traffic is coming through your neighbor's device, so you really want to be sure that they don't get your data. Therefore, it generally is encrypted, and so there is a lot of discussion about the security. Then the beacon and the probe has been modified so that you know what mesh you belong to, and how the protocol, how the packet will be routed. Packets will be routed, and there is 6 address scheme instead of 4. Previously, we talked about 4 addresses. Remember, the transmitter, the receiver, the source, and the destination. Now they have the mesh tunnel beginning, mesh tunnel end, and then the source and the receiver. So the mesh tunnel begins at some point and ends at some point, and then there is a source and the destination, and then there is a transmitter and the receiver. Includes route discovery, route maintenance, and route recovery. So how do you go from one house to the next? They have to exchange some packets to figure out who can hear whom, what is the signal strength, and what is the best path. All that detail is here. And then the hybrid mesh protocol for layer 2 routing combines tree-based routing and AODV routing. So we haven't discussed AODV routing. We will be discussing that when we talk about layer 3 in wireless. So basically, there is a whole set of protocols for routing in the wireless. And 2 of them are, one of them is this tree-based, and one is AODV, distance vector. I forgot AO. Do you remember AO? Anyway, so this is a distance vector routing, and we will discuss this when we have finished all with the data links and we move to the routing layer for wireless, which will be after we have discussed LAN, PAN, WAN, MAN, and so on and so forth. Then we will move to the layer 3. So there we'll talk about the routing protocol, and so that is used in this mesh network as well at layer 2. So anyway, the wireless mesh network again is more theory than practice, and the reason is because 2 reasons. First of all, nobody trusts their neighbors to be forwarding their traffic. Second thing is, nobody is interested in forwarding the traffic for the neighbors because there is no money to be gained. So because there is no economical model for mesh, its use is limited to the 2 things that we talked about, that is the military and emergency response. Yeah.
On the tree-based routing, is that doing something similar to spanning tree?
Exactly.
Okay. And if DV is a distance vector, doesn't that mean that that's a layer 3 algorithm?
Yeah, so what they do is, this is what is happening. Now one more thing which is happening is, everything that was in layer 3 is being moved into layer 2. Now, so for example, you heard of OSPF. OSPF is the layer 3 routing, right? Ethernet has adopted it. So if you buy a latest Ethernet equipment, I mean, you won't buy it probably. If a carrier buys a latest Ethernet equipment, it does routing at layer 2, so that way you can have a country-wide Ethernet. You could have Ethernet where packet is sent from San Francisco to Boston and never leaves the Ethernet layer. Right? So that is another way the layers are breaking down, is that every layer wants to be independent. So basically the Ethernet people don't, I mean basically they want to be independent of the IP layer and they want to be covering the whole area, where while the Ethernet was designed to be local area network, but now they have become wide area network. And so they have adopted the higher layer into themselves. Does that make sense? So basically similarly here, when you have a wireless network, it could depend upon IP and to find the route from A to B, but 802.11 wants to have its own way of finding a route from A to B.
So I guess my wonder here is who precedes who? Is it the layer 2 routing that precedes the layer 3?
Yeah, of course. So what will happen is, here's the thing. Suppose a packet is coming from Japan and going over this wireless networks to China, let's say, just to be extreme, right? So when I want to go from on this wireless network and I still have to do multiple hops, I would use my layer 2 facility. So this will be a one link actually for the IP.
Okay, but doesn't that mean that the wireless router has to either have knowledge of layer 2 or has to forward it to a layer 2 device to do that routing? Because otherwise the router...
Okay, so you are using a name, you are using a term which I have to correct. A wireless router word means it is a layer 3 device. A wireless router or wired router knows IP. Okay? And it will be using the IP layer mechanisms. A wireless access point and a wireless station, they are not supposed to know IP.
Right.
They are doing this routing.
Right.
Alright, so I wouldn't call them wireless router. They are just the access point.
Right.
They are layer 2 devices and they are doing routing.
Right, I understand. My question was if the wireless router has this sort of knowledge to forward or to trust the forwarding function to one of these access points.
Mm-hmm.
So, I mean, because of them mashing the layers now, do they trust each other to do that? Or?
Yeah. So here's what will happen is, so let's say there is a router at the beginning of the wireless network, right? It speaks both layer 3 because it is talking to some wired thing on the other end, right? So it speaks IP. Now it has to send over this mesh wireless. So it is going to give its packet to layer 2. Alright? Now the layer 2 could be just one wireless hop and that's done, that's easy, right? But now it's a multi-hop. So the layer 2 will figure out those multiple hops. For layer 3, it is still the IP header will not be touched.
Okay.
That is just whole thing is one link. Right? So based upon the layer 2 header, this whole multi-hop will take place.
Have they finished this one?
No, this standard will be done. So sorry, 11S. Again, I have to check. Again, I have to check. Expected January 2011. So one more year to go. All right. I think we are done. Any question about 11S before we move to 11T? Actually, I am running out of time. Let me see how much I have left. Plenty of them left. Wow. All right, so let me just then stop right here. We will continue on 11T next time.